This is B. Naresh, working as assistant professor in EC department. And today's topic is, we'll discuss the problems related to diode current and its resistance calculations. So before going to observe these problems on this diode current and its resistances, so we are having that actually basically we are in the two types of the resistances here: static resistance and dynamic resistance here. So we observed in a static resistance, the static resistance is represented as capital RF under the forward direction. It is a ratio of voltage to the current, means it is represented as VF by IF at particular point. So that can be observed from the characteristics of the PN diode. Similarly, the dynamic resistance under the forward bias, it is represented as small rf, and it should be observed with respect to the slope of voltage with respect to your current. From there, it is defined as eta times of Vt by I. So where, and again, we know that in a diode, the diode current equation is represented as I is equal to I naught into e power V by eta times of Vt minus 1 here, where I is the diode current, I naught is the reverse saturation current, and V is the voltage across the diode, eta is a constant, and Vt is the thermal voltage, where eta is, so in a diode, we are the two types of the materials. Either it is constructed with silicon or a germanium. If the diode is constructed with germanium, we need to consider eta is 1 year. If the diode is constructed with silicon, we need to consider eta is 2 year. And again, where Vt is the thermal voltage, and it is represented as Kt by Q, where K is the Boltzmann constant, T is the temperature in kelvins, and Q is the charge of an electron. Then while substituting this K and the Q values, it is also represented as T by 11,600. Just substitute the K value, Boltzmann constant, and charge of an electron. Then it shows that 1 by 11,600 of T, where temperature in T is temperature in Kelvin. So by using all these parameters, now we are going to solve some problems, those related to your diode current as well as resistances here. So we'll see the one by one problem here. So coming to the first problem, determine the forward resistance of a PN junction diode when the forward current is 5 milliamperes at T is the 300 kelvins. And here they state that assume the diode type is the silicon diode. So from this problem, we need to identify the forward resistance of a PN junction diode with the given specifications. So they given the forward current is 5 milliamperes here, means the IF they given that 5 milliamperes, and the temperature T they given that 300 kelvins. So then, and we need to assume the diode type is silicon, means the eta value we need to consider your 2 here. So from this, what are the parameters they given here? They given the diode current. So diode current IF is represented as 5 milliamperes, and the temperature they given 300 kelvins here. Now we need to calculate a forward resistance here. So coming to here, first we need to write the given specifications here, and based on the current is represented as 5 milliamperes, and the temperature they given 300 kelvins, and the eta is a 2, means they are not given the eta, but they assume, we need to assume the diode type is a silicon. So based on this assumption of the silicon diode, the eta value we need to consider to be 2. Suppose if the diode type is a germanium, here we need to consider eta value is your 1 here. So based on that, we need to calculate a dynamic, a forward resistance based on this given specifications here. So we know that from this representation, the resistance is represented as RF is represented as for under the forward direction. So here RF is represented as under the forward direction, eta times of Vt by I. So in this, we need to determine this a resistance, and first we need to identify what are the parameters they specified in the problem here. So in that, they mentioned that I is given here. So where I is 5 milliamperes here, and eta. So the diode type is a silicon, hence we need to consider this eta value is 2. Now we need to calculate Vt. So how to calculate this Vt? So Vt is represented as, we know that, Kt by Q R. So while substituting this Boltzmann constant, where K is the Boltzmann constant, Q is the charge. While substituting these two, then it also represented as T by 11,600. Means now we need to substitute what is the T value given, the T in the kelvins. So 300 divided by 11,600 here. So for this case, I represented this one. Now I substituted this T is a 300 kelvins, and this is 11 by 11,600. That is equal to 0.02586. I represented in terms of millivolts. That is 25.86 millivolts here. So up to this point, we observe the thermal voltage. So based on the given temperature, so for 300 kelvins, the thermal voltage here it is represented as 25.86 millivolts here. Now we need to calculate the resistance for a PN junction diode under the forward bias, and we know that what is the formula for this resistance here? RF is represented as eta times of Vt by I. So now we need to again verify all the parameters are there or not. So eta is a known value, that is a 2 based on the silicon here, and Vt we observe now. What is the Vt value of 25.86 millivolts, and I they given 5 milliamps here. So just you can substitute here. So this forward resistance is eta times of Vt by I, where eta is a 2, Vt is a 25.86 millivolts, means 10 power minus 3, divided by your current is 5 milliamperes, means 5 into 10 to the power of minus 3. Just can solve this one. So here I shown the same thing, where small m indicates that 10 to the power of minus 3. Here also this 5 milli means 10 to the power of minus 3. It gives that, so for simplification, it gives that 10.34 ohms here. Means the dynamic so the resistance under the forward bias RF is represented as 10.34 ohms here. Now we need to verify with theoretically. So we know that when the diode is a forward bias, it offers very small forward resistance here. So that is the reason. So practically based on the given statements, so here also this is the only very small resistance, 10.34 ohms. So this is based on your given statement here. Now we'll see another problem. Find the value of DC resistance and AC resistance of a germanium junction diode at 25 degrees centigrade with I0 is 25 microamperes and at an applied voltage of 0.2 volts across the diode. So here in this problem, now we are going to calculate the two types of the resistances here. One is DC resistance, another one we are going to calculate AC resistance. But they are specifically mentioning that the given PN junction diode type is germanium. Means we need to consider the eta value is 1. Based on this given statement, the eta value is 1. And the temperature, they're given in degree centigrades. So, but we need to convert before to process the data. We need to convert this degree centigrades to your Kelvin. So here, what is this? Your 25 degree centigrade temperature here. So then, where I naught is reverse saturation current here. So here, I naught is represented as reverse saturation current, and at an applied voltage means this is voltage across the diode is 0.2 volts here. So here we need to determine the two types of the resistances here. One is the DC resistance, one is the AC resistance. Here this DC resistance is also called as the static resistance, and the AC resistance is also called as dynamic resistance. So DC resistance means it is represented as capital RF. AC resistance means it is represented as small rf here. So here this DC resistance means simply it is represented by VF by IF, and RF means it is represented as eta times of VT by IA. So by using these two formulas, then we need to identify the DC resistance and AC resistance of a germanium junction diode with respect to your given temperature is 25 degree centigrade. So at this temperature, the current diode allows the reverse saturation current, that is here represented by 25 microamperes. Now first we need to write what is the given values here. So for this case, and the given data is, so where I naught is a reverse saturation current, they are given that 25 microamperes, and the temperature in degree centigrade, that is 25 degrees centigrade, and voltage across the diode they are given that 0.2 volts. And from this given statement, the diode type here. So what is the diode type here? The diode type is represented as your germanium here. And we know that if the diode is made up with germanium, it is represented as eta is the 1. If the diode is made up with silicon, the eta is represented as your 2. Now we need to identify the two types of the resistances here. Now coming to you. So before going to this, so if you observe this one, so we need to first find out the current, how much current here. They are not given the how much current is produced with respect to these parameters here, but they are given that only that reverse saturation current. So before to analyze this static resistance or a DC resistance or AC resistance, first we need to identify that how much current is generates or flowing across this PN junction diode with respect to these parameters here. So hence we need to recall the diode current equation. So what is the diode current equation? So we know that the diode current equation is represented as I is equal to I naught into e power V by eta times of Vt minus 1. And we know that where I naught is represented as reverse saturation current, and V is represented as voltage across the diode, and eta is a constant. For silicon, that value is a 2. For germanium, that is 1 here. Similarly, Vt is thermal voltage, and it is represented by kT by Q. So it is also represented by T by 11,600. So this is T by 11,600. While substituting this K value and a Q value, where K is the Boltzmann constant and Q is the charge of an electron, while substituting these two, it shows that a T by 11,600. But where T is in a kelvins. But in our problem, they given that the T in a degree centigrades here. So if you want to convert the degree centigrades to your kelvins, first we need to, means for that degree centigrade, we need to add this 273. Then it is represented in your kelvins here. So hence, and first I need to calculate this thermal voltage here. And how to calculate this one means based on this one. So in a problem, the temperature they given that 25 degrees centigrade. So here I'm going to convert this degree centigrade to a Kelvin. So hence, for a given degree centigrade, we need to add the 273, that is converts to your Kelvins here. So hence, I added this 25 degrees centigrade with a 273, then it becomes your Kelvins here by 11,600. So it gives that this ratio 25 plus 273 by 11,600 ratio gives that 0.0256. Means I represented in terms of millivolts. Here it is represented as 25.68 millivolts here. So this is the thermal voltage with respect to your given temperature. So what is the given temperature here? The temperature is 25 degree centigrade. Now I'm going to so in this case, if you observe this diode current expression, so the diode current expression contains reverse saturation current. V means voltage across the diode, eta is a constant, Vt is the thermal voltage. So already we in a problem they mentioned I0 value and voltage across the diode, and based on the type of the diode we observe this eta means constant value of PN junction with respect to material, either silicon or germanium. Then Vt we observe here, so means all the parameters we know here. Hence here I'm going to substitute all these values in this to observe the diode current here. So hence just can substitute here. So what is the I0 value? I0 is 25 microamperes, means 25 into 10 to the power of minus 6 e to the power of V means voltage across the diode. The voltage across the diode in a problem they mentioned that 0.2 volts, and by eta is a 1, and the Vt we observed is 25.68 millivolts. Hence I represented this one 25.68 into 10 to the power of minus 3, and this is minus 1. Just can solve this one, then it shows that the current is 60.2 milliamperes here. So here the current is represented as 60.2 milliamperes. So this is your I. So based on the given statements here, the current in a diode is represented as 60.2 milliamperes here. So by using this current, now we need to calculate the two types of the resistances here. One is DC resistance, another one is your AC resistance here. So hence, now I'm going to calculate first the DC resistance here. So what is the DC resistance here? The DC resistance is represented as RF is, it is the ratio of voltage to the current. So where V is voltage across the diode, I means the current across the PN junction diode. So just now we observe this I, and we already mentioned in the problem here. So what is the V mentioned here? V is represented as 0.2 volts divided by I. Just now we got the I. What is I value? I we observed 60.2 milliamperes here. So hence, so here I am going to write this I is the 60.2 milliamperes here. So hence, so 0.2 divided by 60.2 into 10 to the power of minus 3. Then you can solve this ratio. It gives that the resistance is the DC resistance, or it is also called as your static resistance. So here it is represented as 3.33 volts here. So always you can verify that with the theoretical values. So we need to match the practical values also here. So we know that when the diode is a forward bias, it offers very small forward resistance. If it is a reverse bias, it offers the very large reverse resistance here. So from there, you can verify, you can cross verify that it is related to forward resistance or not here. So based on this, we observe this a diode DC resistance or a static resistance based on the given problem statement values. So here this DC resistance is represented as 3.33 ohms here. Now again in the problem, then they also ask that to determine the AC resistance here. So what is AC resistance? It is represented as a small RF that is equal to eta times of Vt by I, where eta is a constant, and we know that eta is a 1 for germanium and eta is a 2 for silicon. And again Vt is the thermal voltage. Just now we got this one, that is kT by Q or T by 11,600 here. So based on a given temperature, just now we observed the thermal voltage, and I means the diode current here. So we also observe this diode current here. So what are the values we observed here? Where the Vt is, so Vt is we observed 25.68 millivolts, and I is so 60.2 milliamperes here. So Vt value is 25.68 millivolts and I value is 60.2 milliamps here. Now we need to substitute these values in this AC resistance representation here. So what is AC resistance? Eta times of Vt by I, where eta is constant. Means in the problem they mentioned that the diode type is germanium, hence we need to consider that is 1. So hence here I consider eta value is the 1 and the Vt is 25.68 millivolts, or so this is 25.68 into 10 to the power of minus 3. It is also represented as 0.025668 here. So hence I substitute this 0.02568 by I value we observe that 60.2 milliamperes here. So milli means 10 power minus 3. Just can solve this ratio, then it gives that AC resistance is 0.42. The units are your ohms here. So up to this point, we observed the DC resistance and AC resistance based on a given problem statement here. So the DC resistance is 3. So we observe this DC resistance is 3.33 ohms and the AC resistance is we observe 0.42 ohms based on a given problem statements here. Now we'll see another problem here. Calculate the dynamic forward and reverse resistances of a PN junction diode when the applied voltage is 0.25 volts at T is 300 kelvins, given I0 is 2 microamperes. Assume the diode type is silicon here. So means we need to again in this problem we need to find out the dynamic forward as well as your reverse resistances here based on a given parameters. So what they given here, the parameters are the applied voltage is across the diode is 0.25 volts here, and where the temperature is 300 kelvins here, and I0 means the reverse saturation current. The reverse saturation current is 2 microamperes and the diode type is silicon here. So means we need to consider the eta value is 2. So here the diode type is silicon, hence we need to assume eta value is 2. Suppose in some of the problems they are not mentioning the type of the diode. So in that situation, you can choose your own assumption. Either you can choose either the diode type is a silicon or you can choose the diode type is germanium. That is your choice. So based on your assumption, suppose if you are assuming that the diode type is a silicon, you should consider the eta value is 2. Suppose if you are consider the diode type is a germanium, then you can assume the eta value is 1 here. So but here I mentioned that one. So what is the type of the diode? But if they are not mentioned, then first you can choose that what is the type of your diode. Either it is made up with silicon or your germanium. Based on your assumptions, you can assume that the eta value is either 1 or 2. But in our problem here, they mentioned that the diode type is the silicon, hence we need to consider the eta value is 2 here. Now first we need to write what is the given problems, what is the statements here. So for this case, here I am writing. So they given that the reverse saturation current, the reverse saturation current is I naught. So that is a 2 microamperes here. And temperature is 300 kelvins. And voltage across the diode is 0.25 volts here. Now we need to assume the eta value based on the type of the diode, that is the silicon diode. Hence, we need to consider the eta value is 2. So based on all these parameters, we need to calculate the two types of the resistances here, dynamic forward and reverse resistances of this PN junction diode. So before going to this, first we need to identify. So you can observe here, if you want to calculate either a forward resistance or a reverse resistance, we need to identify the current, diode current. But in this problem, they are not mentioned the diode current, but they mention the reverse saturation current. So before going to process either any resistance, first we need to know the how much current is delivered across the PN junction diode. For this case, first we need to determine the diode current here. Now we know the relation with respect to your reverse saturation current and the diode current. So what is the relation in a diode current here? So I is represented as I naught into e power v by eta times of Vt minus 1. Again here, where I naught is the reverse saturation current, I naught is the reverse saturation current, and V is the voltage across the diode. Or again, eta is a constant, and we know that eta value is a 1 for germanium and a 2 for silicon. Vt is the thermal voltage, and it is represented as kT by Q, where K is the Boltzmann constant, T is the temperature in a Kelvin, Q is the charge on electron. Then it shows that value you're substituting this Boltzmann constant and charge of an electron, it shows that T by 11,600. So if you observe in our problem statement, they mention the reverse saturation current I naught, V is also they mention, eta is also mentioned, and only the unknown parameter is your Vt. So first we need to determine, to observe this I, first we need to calculate what is the thermal voltage based on your given temperature here. So hence, first we need to calculate the thermal voltage here. So what is the formula for thermal voltage here? So Vt is equal to kT by Q or T by 11,600. So where the T is again temperature in your kelvins. So in a problem, directly they mention the temperature in kelvins here. Hence, so 300 Kelvin they mention. So hence I substitute this T value is a 300 by 11,600, that is equal to 0.02586. That is represented as, in terms of millivolts, the value I represented as 25.86 millivolts here. Now, so we got this thermal voltage, and remaining all the parameters are required to determine this I already mentioned in a statements here. So hence, now we are going to calculate how much current is generates across the PN junction diode. So hence, I am going to recall this equation again here. So here, I am going to substitute what are the values are they given here. So I naught is they given 2 microamperes here. So I naught value is 2 microamperes, 2 into 10 to the power of minus 6, and e to the power of V means the voltage across the diode, they given that 0.25. divided by eta value. So here the diode type is they given the silicon, hence the eta is the 2 here. VT just now we observed. What is the VT value here? 25.86 millivolts here. So 25.86 into 10 to the power of minus 3, and this is minus 1. Just simplify the statement here. So then it shows that the current is 0.24 milliamps here. 0.24 milliamps. To solve this simplification, then I shows that 0.24 milliamps. Now by using this current, now we are going to identify the resistances here. So first, I'm going to calculate this dynamic resistance under the forward bias, and we know that the dynamic resistance under the forward bias is represented by eta times of Vt by I. And here, first we need to verify all the values are there or not. So eta is a constant, we know that, and Vt we observed here, and I value also we observed here. So what are the values we observed here? Vt is 25.86 millivolts and I is 0.24 milliamperes here. Now these two I'm going to substitute in a dynamic forward resistance. So hence, so again eta value is based on the type of the diode. So in our problem they mentioned that the type of the diode is a silicon. Hence here we need to consider this eta value is 2. So hence I represented eta is a 2, Vt is 25.86 millivolts. Otherwise you can write in terms of 0.02586. So we got this 25.86 millivolts, or otherwise this is 0.0258 divided by I is 0.24 milliamps. So milli means 10 to the power of minus 3. So simplify this ratio, it gives the dynamic resistance is 215.5 ohms here. After the simplification, it shows that the dynamic forward resistance is 215.5 ohms here. So apart from that, in a problem, they also ask that one more statement, that is a reverse resistance here. So here, so we need to calculate that reverse resistance. So if you want to calculate the reverse resistance, so we need to calculate this RR. Otherwise, you can write capital R with suffix R. So reverse resistance means it is observed under the reverse bias, and we know that under the reverse bias, it does not offers a majority current, but it offers a minority current that should be represented in your reverse saturation current. Hence, we know that this is V by your I naught. So what is the V value they given? The V value they given that in a problem. If you observe the problem statement, so V value is a 0.25 and I naught is 2 microamperes here. So hence, so here we need to calculate. So here this is V is 0.25, I naught is 2 into 10 to the power of minus. So this is your reverse resistance. 0.25 divided by 2 into 10 to the power of minus 6 means this is what happened, 0.125 into 10 to the power of 6 ohms. 10 to the power of 6 ohms here. Now you see another problem. A PN junction diode has a reverse saturation current of 30 microamperes at a temperature of 125 degrees centigrade. At the same temperature, find the dynamic resistance for 0.2 volts bias in a forward and a reverse directions here, and assume the diode type is Germanium. So here we are going to calculate again. We need to find out the dynamic resistance here based on these statements here. So for this case, they mentioned that the reverse saturation current is 30 microamperes, and again here the temperature they mentioned in degree centigrade. But suppose if you want to calculate the thermal voltage, now we need to convert this degree centigrade to your Kelvin by adding the 273 for this degree centigrade here. So first I'm going to write what are the given parameters here. So means I naught is 30 microamperes, means reverse saturation current is 30 microamperes, and temperature they mentioned 125 degrees centigrade, and voltage is 0.2 volts here. So now we need to consider the type of the diode is germanium, means the eta value we need to consider here 1 here. Now we need to calculate the required parameters. So if you want to calculate I, so we know that what is I here? I is represented as I naught into e power v by eta times of Vt minus 1. So first we need to determine this thermal voltage. So we know that the thermal voltage is represented by KT by Q. While substituting this Boltzmann constant and a charge and electron, it gives that either T by 11,600. So here also I mentioned the same point. But in a problem, they given the temperature in degree centigrade. So to process this one, first we need to convert this temperature in a Kelvin. So hence, what I need on here, 125 degrees centigrade is added with the 273, then gives that Kelvins. So hence, 125 plus 273 divided by 11,600, it gives that this ratio gives that 34.3 millivolts here. 34.3 millivolts here. So by using this thermal voltage, now we are going to calculate the diode current here I. So what is the expression? So I is equal to I naught into e power v by eta times of Vt minus 1. Now we need to verify I naught already they given here. So what is I naught value they given in a I naught here? They given that 30 microamperes here, and the voltage is 0.2 volts here. So hence, so here I naught is 30 microamperes, V is a 0.2 volts, and the eta is the type of the diode is, what is the type of the diode here? The type of the diode they mentioned in Germany, means we need to consider the eta value is 1 here. So hence here, so V is a 0.2, eta is a 1, Vt already we observed 34.3 millivolt. So now we are going to substitute all these parameters to determine this diode current here. So hence, so I naught means 30 micro, 30 into 10 to the power of minus 6, e to the power of V means 0.2 volts. Eta is the type of the diode is germanium, hence I consider 1. Vt was just now we got this 34.3 millivolts, means 34.3 into 10 to the power of minus 3 minus 1. Just simplify this one, then if we observe this 10.18 milliamperes with respect to your given specified parameter. So I means the diode current is 10.18 milliamperes here. So by using this now, we are going to calculate the how much forward dynamic resistance is offered with respect to your given specifications here. So for this case, based on this one, we know that the dynamic forward resistance is represented as eta times of Vt by I, where again eta is a constant based on the germanium or silicon. If it is germanium, that we need to consider 1. If it is the silicon, we need to consider 2 here. And Vt is the thermal voltage and I is the current. So Vt we observe, I also we observe. Now eta is a constant value. Now we need to substitute these three stress parameters to observe this dynamic forward resistance here. So here, so we know that eta is a 1. Why? Because of that, in a problem, we mentioned that the type of the diode is germanium. Hence, I consider the eta value is a 1. Vt we observed 34.4 millivolts, hence 34.4 into 10 to the power of minus 3. And just now we got the current. What is how much current here we observed here? The current is 10.18 milliamperes. So hence, I'm going to substitute this in this case. So here the current is 10.18 into 10 to the power of minus 3. Just solve can all these to this ratio 1 into 34.4 into 10 to the power minus 3 divided by 10.18 into 10 to the power of minus 3 here. Then it gives this, the ratio is 3.379 ohms. So this is equal to your RF, dynamic forward resistance here. The dynamic forward resistance is 3.379 ohms here. Now another problem is, so here just can observe the statement. If the two diodes are connected back to back and the voltage V is impressed upon, calculate the voltage across the each diode and the current through each diode. Assume the similar value of I0, that is 1 microamperes, for both the diodes and eta is 1. So this is the given circuit diagram here. So in this case, so here the statement, the two diodes are connected back to back. So here these two diodes D1 and D2 are connected back to back, and this voltage is passing through this D1 and D2. So we need to calculate the voltage across each diode D1 and D2. It means how much voltage is the voltage across the D1 and how much voltage is flows across the D2. So hence from this problem we need to determine this VD1 and VD2 along with the current. So for this case they assume that the reverse saturation current is 1 microamperes and the diodes, the silicon means eta values also they consider 1, means these two diodes are made up with germanium. So that is the reason we consider this eta is 1 here. And we know that due to this applied bias, if VD1 becomes what happens here, so positive voltage is connected to cathode, means the D1 is acts as your reverse bias here. So if it is the reverse bias, it offers you the reverse saturation current, that is 1 microamperes. That 1 microampere current is also flowing through this D2. So that is the reason the current across this D2 is also your same here. So from that point I represented here. So based on your applied voltage, just you can observe this one polarity here. The positive polarity is connected to cathode of D1, hence D1 becomes your reverse bias. So that is the reason D1 is the reverse bias. So that if it is a reverse bias, that particular diode offers only the reverse saturation current. So in the problem, they mentioned that the reverse saturation current is 1 microamperes. Hence, the current across the D1 is 1 microampere. Similarly, with respect to this biasing voltage, now this D2 of anode is connected to positive pole of this battery source. Hence, D2 becomes your forward bias. So if the D2 is a forward bias here, then how much current is there here in the circuit? These two are connected back to back, means here it offers the reverse saturation current, that is 1 microamperes. The same current is flowing through this D2 ends. So forward current is equal to your reverse saturation current. So that is the reason I is equal to I0. I consider here 1 microamperes. That is now voltage across the D2 is VD2 here. Now we need to calculate the voltage across the D1 as well as your D2 here. So for this case, and we know that this is I is equal to I0 into V by eta times of Vt minus 1. Now I'm going to first calculate the voltage across the diode D2. So hence, here I represented with V is replaced with VD2 here. And this is similarly I is equal to I0 is I0, only the I replaced V, voltage across the diode. Which diode I'm going to observe here? Your D2 is a forward bias, hence I'm going to first observe the voltage across the diode D2. Hence this V is replaced with VD2 by eta times of Vt minus 1 here. So we observe this, the I is 1 into 10 to the power minus 6. I0 they given that 1 microamperes here. Now e power Vd2 by eta times of Vt minus 1. So from this, so eta is 1 here, then Vt is the thermal voltage. Now we can find out this ratio. So after simplification, we got this one. This e to the power of Vd2 by eta times of Vt, that is equal to your 2. Just can simplify this all these parameters here. Then it gives that this 2. Then you can simplify this ratio. So that exponential taken on this side, it becomes a ln here. Now here, that is Vd2 is equal to eta times of Vt into ln of 2 here. So where eta is a 1 and Vt is according to room temperature, we know that according to room temperature, the Vt value is approximately equal to your 26 millivolts here. So hence, I consider this VT value at room temperature. At room temperature, the thermal voltage is 26 millivolts and this ln of 2 becomes 0.693. After this simplification, the voltage across the diode D2, we observe that 18 millivolts here. Means the VD2 voltage is 18 millivolts here. Now, suppose if you want to calculate this VD1, so if you observe this one, so the voltage means if you observe the circuit, so this V is equal to VD1 plus your VD2. From the circuit, the applied input voltage is passing through your VD1 and your VD2. From that, I represented this V is equal to VD1 plus your VD2. Hence, from that representation, I calculated this VD1 is equal, means V is equal to VD1 plus VD2. So here I am going, VD2 already we observed that VD2 is 18 millivolts. We already mentioned here. So means we need to calculate this VD1. So VD1 is equal to V minus your VD2. So hence VD1 is equal to V minus, that is, so actually this is 18 millivolts means 0.018 here. So this is V minus 0.018 here. So that is voltage across your VD1 here. So up to this point, we identify the problems related on diode resistances and the diode current expression here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.